Okay, let us start to do this question. Is about heat. So, a 125-gram block of unknown substance with a temperature of 90 degrees Celsius is placed into a styrofoam cup containing 0.326 kilogram of water at 20 degrees. So, what we can do is just we first highlight all the important parts. So this is the important part, starting with 20 degree, temperature 90 degree, and the system reach an equilibrium. So this is very important. It reach an equilibrium temperature of 22.4 degrees Celsius. What is the specific heat capacity of the unknown substances of the cloud? Okay, and it's stated that the uh, heat capacity of the cup is negligible. Okay, so what we want to do is we state everything down. So we have a 125 gram of block with an unknown substance. So it's a mass 1 equals to 125 gram, and it's also 0.125 kg. So it's very simple. Starting degree Celsius, theta I is going to be 90 degrees Celsius. So this is the first object one, and the second object as a M2 is 0.326 kilogram, and the starting temperature of I is 20 degrees Celsius. Okay, so the system reach an equilibrium for this one, so both of them will reach an equilibrium. So this one of F is equals to 2.4 degrees Celsius. So what we're gonna do? What we know is that the input energy minus the output energy is output. What am I spelling? Output energy is must be equals to 0. On the other words is mc theta, or we can say final temperature minus initial temperature is equals to mc initial temperature minus final temperature of the other substances. The negative, why I didn't say negative, because I just take it away. So it should be the final minus initial, but I just change it around so you can understand. You can write it down more simpler lah. So write it down everything. So m is 0.125 for the first object, and c is the one you want to find. Okay, theta is 90 minus 22.4. So this is the first object. The second object is 0.326, and the c will be, because it's water, so 4200, and this one will be 22.4 minus 20 degrees Celsius. Okay, it's just another way around, but it's also the same. Okay, so after that, once we already do this, we can just write it down, calculate. So this one, the result over here will be 0.125 times 67.6, so 0.125 c, and this will be 67.6, and here when I calculate it will be 3286.08. Okay, so this one will be 8.45. Okay, c equals to 3286.08, and the specific capacity will be 389, around 389 joule kg, -1, and c, -1. So this is your answer for the first question. Okay, so this is your answer for the question. So as a reminder, we need to understand is that when we say it's equal sign, it must final minus initial, initial minus final for both objects. So different object, you write differently. So both will be positive lah. Okay, you can just take it around over there. Okay. How about the next question? Let's do the next question. Okay. Next question talk about the effective power of oven is 1500 watt. Okay, the temperature of mass is 160. Okay, which again is water. Instead, some food rises from 15 degrees Celsius to 90 degrees Celsius. Calculate the time taken for heat temperature specification. This one. Okay. So again, we write down everything. The power will be 1500 watt. The temperature, not temperature, mass. The mass will be 160 gram, and it equals 0.16 gram. Not gram, sorry, kg. Okay, the temperature change in temperature, it will be minus 15, and you will get 75. 75 degrees Celsius. The specific capacity C is 4200. So what do you want to find? Time, T is how much? So first we need to define is the energy. Why? Because power equals energy divided by time. So if we find energy, we can find the time. So what is energy? So energy equals to mc theta. So m is 0.16, c is 4200, and theta will be 75. Okay? And this one, if we calculate, we can get the answer of 50400 joule. Okay, and we put inside over here, so time equals energy 50400 divided by 1500, and we can get the time is around 33.6. Okay, 33.6 seconds. So this is your answer for the second question. Okay, so you need to still memorize the formula for power equals energy over time. Then you can do. Okay, let's continue with the question number 3. Let us read the question. An electrical heater is placed in an insulated container holding 100 grams of ice with a temperature of negative 14 degrees C. The heater is supplied energy at the rate of 98 joules per second. After an interval for 30 seconds, it reaches a temperature of 0. Calculate the specific heat capacity of ice. So what we're going to do first is writing out, labeling all the information that he gave us. First thing first, he says that 100 grams of ice, so the mass is 100 grams. In other words, is 0.1 kg because we divide by 1000. The other one, the temperature, initial temperature is negative 14 degrees C, and the final temperature is going to be is 0 degrees Celsius, and the change in temperature is 14 degrees C. Okay. Next thing, it says that the electrical heater supply energy rate of this one 98 joules per second means that the power is actually 98 watts per second. So joule per second means watts, and after 30 interval of 30 seconds, so means time is 30. Okay, so what we want to do is we want to find C. So in order to find C, we need to know that the formula is energy equals to mc theta, and the other formula that we know to find energy is power equals energy over time. So first we need to find energy. So power times time equals energy, which is 98 times 30 seconds equals your energy, and energy is also equals to mass is 0.1, c, and theta, change in theta is 14 degree. Okay, so 98 times 30, we get the answer of, let me calculate, it's 98 times 30, so we get 2940, and divided by 0.1 and 14 degrees Celsius equals C. So our C equals to 1200, okay, 1200, the unit for C is joule per kg per degree C. Okay, so this is your answer for number A. Okay, let me minimize all these things so that you can see more clearly later on other answer. Okay, so second part B, the show the final temperature of water formed when heater left for further 500 degrees is about 40. So we need to prove that the final temperature is about 40. Okay, first thing first, we need to find energy. So we know that energy is equal to mc theta, and energy is, the other formula for energy is power equals energy divided by time. So power times time, power again is the same power, is 98 times the second is 500. Okay, and is equals to energy. So 98 times 500 is equals to 4900 equals energy. So let us think what is the energy meant by here, because the energy is like from 0 degrees Celsius to 40 degrees Celsius, but it's still in ice form. So before converting from the 0 degrees Celsius to 40 degrees Celsius, we need to start that the total energy spent is from ice to become water with 0 degrees Celsius, and from water to 40 degrees Celsius water. So there's a two-step process. So the total energy will be energy for ice to water, and the energy for 40 degrees Celsius. And the formula for that is, for ice to water is ml, and for 40 degrees Celsius is mc theta. Okay, so what is m? So M is already same 0.1, and L is the latent heat here already stated. Then the latent heat of fusion is around 3.3 times 10 to the power of 5. So 3.3 times 10 to the power of 5 plus M is also 0.1, C is 4200 because this is water and not ice. Okay, 4200, this is water, not ice, and 40 degrees Celsius. So no, we're going to prove it's 40 degrees Celsius. So final temperature minus initial, which is 0. Okay, so let us prove it. So this one is for 49000, my mistakes. Okay, so 49000 minus 0.1 times 3.3 times 10 to the power of 5 is around 33000. Okay, and equals to 0.1 4200 and degree F. Okay, so 49000 minus 33000 is 16. It's 16. Okay, and divide that by 0.1 and 4200, and this is F. So let us try to do it. Divided by 0.1 and divided by 4200, we get is around 98 degrees, which is similar to 40 degrees. Okay, so this is how we prove it. So we need to prove. Okay, so there's two step process from ice to water and from 0 degrees Celsius to 40 degrees Celsius of water. Okay, so this proof the second one. Okay, let me minimize again so we can continue the small space to do other question. Okay, so the third question is the whole procedure repeat in an insulated container at room temperature at 25 degrees Celsius. State, explain or show whether the final temperature of water formed would be higher or lower than the calculated in B. Okay, what do you mean by that? So at the beginning we try to do this experiment without thinking about environmental factor. But now we have an uninsulated container, means the environment will provide energy towards the ice or the water. So let us think that way. Okay, so starting we know that if it's from water to ice, not water to ice, sorry, water from 0 degrees Celsius to water for 40 degrees Celsius. Okay, 0 degree and 40 degree. So in the room temperature is 25 degrees Celsius. In room temperature in the 25 degrees Celsius. So if this is a cup of water, okay, this is a cup of water for 0 degrees Celsius, and the environment is 25 degrees Celsius, who will supply the energy to who? So we know that the energy supply will be from the environment, which is 25.0 degrees Celsius, will supply to the surrounding, supplied by the surrounding towards the water. Okay, so from 0 to 25 degrees Celsius, it will supply from surrounding to water. And after 25 degrees Celsius towards 40 degrees Celsius, it will be water supply to surrounding. Okay, by this fact we can understand that that period of time from 0 degrees Celsius towards 25 degrees Celsius is actually total of 25 degrees Celsius, which is a lot more than the 15 degrees Celsius from water to the surrounding. So at that time we know that 25 degrees Celsius is much bigger than 15 degrees Celsius, which we can say that the final temperature of water form should be higher, because we know that the energy supply is around 40,000, 49,000, but at that time, at that 0 to 25 degrees Celsius, at that time, the surrounding will supply water, supply energy towards the water, which lower the requirement from 0 to 25, and from 25 to 40, it will release 15 degrees Celsius of the energy from 25 to 40. So we can understand that the energy supply from the surrounding is much higher than the energy wasted from 25 towards 40, which can increase the energy because it's starting with 49, but now it's lower than 49 because some of the energy is supplied from the surrounding towards the water, which lower the temperature required to reach 40 degree. And it will reach higher degree if we continue using 49, we continue using 49k of joule of energy. Okay, so this is how is it. Okay, let's do next question. Next question is about a container hold 42 cm cube of water, 90 degrees Celsius, metal cube, so it's cube, initial at 0, added into water. Each metal cube had a size of to this one, density of this one, and a specific capacity of 400. Water is 4200. No heat loss surrounding. How many metal cube? How many metal cube? So it's important is asking how many metal cube. Okay. So this one temperature final mixture become 20 degrees Celsius. So what do we mean by this? A lot of information, so we're gonna draw it down so it become more simpler. So starting this water starting at 42 cm cube with a 90 degree, going to become 20 stellar over here. Okay, and inside we put a metal cube. So how many metal cube we put inside is the question asking. So one metal cube is a length of 2 cm, okay, density of 8.0 gram, and the specific capacity C is 400 joule kg minus 1 C minus 1. So let us solve this question. Okay, so first we want to write down everything. So we start from water. So water is have a volume of 42 cm cube. The temperature change is from 90 to 20, so it's different from 70. So I say 90 minus 20 lah. Okay. And what we have, the C is 4200, and this is what we know. Okay. So all the information is over here. And density of water is given us. The density of water is 1 gcm minus 3. So this is the density of water. So how about the metal cube? So a metal cube starting with a length of 2.0 cm, which the volume is is cube of the length, and we get 8.0 cm3. Okay, and then degrees Celsius, you start from 0, is stated 0, and we want to go to 20 degrees Celsius. The change is 20. Okay, and the specific capacity it gave us is 400 kg minus 1 C minus 1, and the density is 8.0 gram cm cube. Okay, this is not a tricky question. It just means to understand what we want. So in order to make it equilibrium, we know that energy released equals to energy absorbed. Okay, just a negative sign lah. So if you want to find the energy, we need to use MC theta. We need to find the mass. Okay, we want to find the mass. So here it doesn't have mass, so we're going to find the mass first. Okay, so let's find the mass of water. Okay, so let's find the mass of water. So I'll move it on top of here, and you can see much clearly. Okay, and here, and move it over here, so you can see much clearly. Okay, so let's see what is the mass of water. So we have the density of 1 and the volume on this side. So we know that density is actually mass divided by volume. So density times volume equals mass. So what we do is 1 times 42, we got 42 gram, because it's 1 gram per cm cube, and it's equals 0.042 kilogram. Okay, how about the cube? The cube stated also the same. Density is 8, so density is mass of volume. So density times volume equals mass. So density is 8, volume is 8, so it's 64 gram. So it's also 0.064 gram kg, not gram. Okay, so once you have both already, we need to find energy equals energy. So, but before that, it says how many metal cubes. So one metal cube is not sufficient enough to lower the temperature of the water to become that. So I will just put a number sign over there. So it says how many metal cube. What do I mean? So first thing first, you write down the mc theta equals mc theta. So for the liquid, for the water, we just write it down lah. So 0.042, C is 4200, and the temperature change is 70. How about the other one? So for the cube, we need to find N, because number of metal cube times 0.064, and because C is 400 and the metal cube is 20. So we're going to do, we move things around. So 0.042 times 4200 times 70 divided by 0.064 times 400 times 20, and you get answer N. So N will be, oh, 24.1. Okay, 24.1, and it's around 24 cube lah, around 24 cube. So this is our answer. Okay, let us continue for question number 5. Let me read the question. A steel railway track installed on a day when the temperature is 15 degrees C. At the end of the trails are fixed tightly so that the rail cannot expand or contract. Okay. During a hot afternoon, the temperature rises to 45 degrees Celsius. Calculate the thermal stress developed from the steel rail. Okay, so we have zero information on how to calculate. Let us read the question and continue. So determine whether the rail will fracture if the tensile strength of the steel is 3.0 times 10 to the power of 8 Newton meter -2. Take the Young modulus will be 2.0 times 10 to 11 Newton meter. Coefficient linear expansion is this. Okay, so let's solve this question. So we write down all the information we get. Okay, all the information we get. So temperature difference is around 30 degrees Celsius. And what do we still have? The tensile strength means the maximum stress we can handle is this one, max stress. Max stress is around 3.0 times 10 to the power of 8 Newton meter -2, and the Young modulus Y is 2.0 times 10 to the power of 11 Newton meter -2, and coefficient of linear expansion is an alpha. It's 1.2 times 10 to the power of -5 degrees C if 1. Okay, so let us see the formula what we have. So first is calculate the stress. So we want to find stress. Okay, max stress and stress is different. Stress is the current stress we're handling, and max stress is the maximum stress that we can handle. So we want to find stress. So Young modulus formula is stress divided by strain. So in order to find stress, we need Young modulus and strain, but we don't have the value for strain. So what is strain? So strain is actually delta L over L. So by using the coefficient of linear expansion, is change of L equals to alpha L delta T. So if we say change of L divided by L is alpha change of T. So by using this formula, we can find the strain and we can find the Young modulus, because you see strain over here is actually the same formula by using the coefficient of linear expansion. Okay, so let's do it. So we can say Y is equals to stress by strain. Okay, Young modulus strain is alpha change of T equals stress. So Young modulus is 2 times 0 times 10 to the power of 11. Alpha is 1.2 times 10 to the power of -5. 10 to the power of -5, and change in T is how many? 30 degrees Celsius equals stress. Okay, so by using the formula, let me calculate using the formula. 2 times 10 to the power of 11 times 1.2 times 10 to the power of -5 times 30. So what is the answer? It's 7.2 times 10 to the power of 1 2 3 4 5 6 7. Okay, and stress is Newton meter negative negative 2. So this is stress. Okay, so we have find the value of stress. Determine whether rail will fracture with the tensile strength is this one. So 7.2 times 10 to the power 7 is much lesser than 3.0 times 10 to the power 8. So it's much smaller. So it's much smaller means that it doesn't fracture because it's still in the limit of tensile strength. So no, it will not fracture. Okay, because the stress is lower than the tensile strength. Okay, so this is the answer. Okay guys, we already reached our last question. Let's read the question. A glass flask has volume of 500 cm cube at 20 degrees Celsius. Fill up with liquid at this temperature. The temperature is then increased to 60 degrees Celsius. The coefficient of the volume expansion of the liquid is 45 times 10 to the power negative 4 degrees C negative 1. And coefficient of linear expansion, the coefficient of linear expansion is this 9.0 times 10 to the power negative 6. Calculate the apparent increase. So we need to label all things down. The first thing we know that the volume of the glass is 500 cm cube, okay, at 20 and increase to 60. So if you increase to 60, we can say the change in temperature is actually 40 degrees Celsius lah. Okay, the coefficient of volume. The coefficient of volume means B and a beta. So the beta is for the glass, is it? The liquid. The liquid is 4.5 times 10 to the power negative 4 C negative 1. And the linear expansion, so it's linear, is alpha for glass is actually 9.0 times 10 to the power negative 6. So because of that, we need to convert. Okay, we need to convert, which is times 3, and we get the value around 2.7 times 10 to the power negative 5 C negative 1. So this is what is this? So this is actually beta for gas. Okay, beta for gas. So what is the formula for the apparent increase of volume? The apparent increase of volume can state that means change in L, not change in L, change in V is actually V times beta of L minus beta of gas, bracket, and change in T. So this is the formula. Okay, so this is the formula we have. Okay, this is the formula we have. So in order to calculate this, let us list down all the things. Okay, so change of V is what we want to find, and V is 500 cm cube. So in order to convert into it, we can still remain 500 degrees C. This doesn't change at all. 500 degrees cm 3. Okay, yep, there's no need to change. Okay, and the beta, this one minus this one, is actually 4.5 times 10 to the power negative 4 minus 2.7 times 10 to the power negative 5. Okay, and change in T is 40. Okay, so this one calculate, this one, so the answer will be 8.46 cm cube. So this is the answer. Okay.